Electric vehicle batteries are at the heart of the transition to sustainable transportation. As the primary energy source for EVs, these batteries not only power vehicles, but also play a critical role in determining their range, performance, and environmental impact. With the rise in global demand for electric vehicles, understanding how EV batteries are made is essential to appreciating their role in shaping the future of mobility. This video explores the step-by-step process of creating EV batteries, from raw material extraction to final assembly. It highlights the challenges faced during production and the innovative solutions paving the way for a greener and more efficient EV ecosystem. Materials used in EV batteries. The production of EV batteries relies on a complex combination of materials, each playing a crucial role in their performance, safety, and longevity. Understanding these materials is essential to appreciating the intricacies of EV battery manufacturing. Number 1. Core components. Lithium. A key element in lithium-ion batteries, it serves as the primary medium for ion transfer between the anode and cathode, enabling energy storage and release. Cobalt, used in cathodes to stabilize the structure and extend battery life, though efforts are underway to reduce or eliminate its use due to cost and ethical concerns. Nickel enhances energy density and improves the range of EVs, making it an essential material in high-performance batteries. Manganese, often combined with nickel and cobalt in cathode chemistries for improved thermal stability and cost reduction. Graphite, the most commonly used anode material, providing a stable structure for lithium ions during charging and discharging. 2. Cathode materials. The cathode is one of the most important components in determining a battery's energy density and performance. Common materials include lithium nickel, manganese, cobalt oxide, NMC, balances energy density, safety, and cost. Lithium iron phosphate, known for thermal stability, safety, and affordability, but with lower energy density. Lithium nickel cobalt aluminum oxide, NCA, high energy density, often used in high-performance EVs. 3. Anode materials. The anode facilitates the storage of lithium ions during charging. Materials include graphite, predominantly used due to its high stability and performance. Silicon-based anodes, emerging as a high-capacity alternative, though still under development to overcome expansion issues. Lithium titanate, LTO, offers excellent safety and fast charging capabilities, but lower energy density. 4. Electrolytes. Electrolytes serve as the medium for ion movement between the cathode and anode. Types include liquid electrolytes, typically a lithium salt dissolved in organic solvents, offering good conductivity. Solid electrolytes, used in solid-state batteries, improving safety by eliminating flammable liquids. 5. Separators. The separator is a critical safety component, preventing direct contact between the anode and cathode while allowing ion movement. Materials include polyethylene, PE, and polypropylene, PP, commonly used due to their thermal stability and durability. 6. Conductive additives and binders. Carbon black or graphene enhance conductivity within the electrodes. Binders hold active materials together, ensuring mechanical stability. 7. Enclosure and cooling materials. Aluminum and steel casings protect the battery cells and provide structural integrity. Thermal management materials include coolants and heat-resistant compounds to regulate temperature. Battery cell design and architecture. The design and architecture of EV battery cells are central to their performance, efficiency, and safety. Each battery cell is meticulously engineered to maximize energy storage while ensuring durability and reliability under various operating conditions. This section delves into the components, types, and considerations involved in battery cell design. 1. Types of battery cells. Battery cells are the fundamental building blocks of EV batteries, and their design varies depending on the application and desired characteristics. Cylindrical cells, most commonly used in consumer electronics and some EVs, e.g. Tesla. Features a rolled electrode assembly encased in a cylindrical metal shell. Advantages: high mechanical stability, efficient heat dissipation, and scalability. Disadvantages: lower energy density per unit volume compared to prismatic cells. Prismatic cells, rectangular in shape with layered electrodes, common in modern EVs due to their compact design and higher energy density. Advantages: better packaging efficiency, easier thermal management. Disadvantages: more prone to swelling under prolonged use. Pouch cells, flexible packaging that can adapt to various shapes and sizes. Advantages: high energy density, lightweight, and customizable. Disadvantages: more susceptible to mechanical damage and swelling. 2. Internal components of a battery cell. Each battery cell consists of multiple layers that work together to store and release energy efficiently. Cathode, positive electrode made from materials like lithium nickel manganese cobalt oxide, NMC, or lithium iron phosphate, LFP, determines energy density and safety. Anode, negative electrode typically made from graphite with emerging materials like silicon and lithium titanate, influences battery lifespan and charging speed. Separator, a thin, porous layer that prevents direct contact between the cathode and anode while allowing ion flow, enhances safety by preventing short circuits. Electrolyte, a liquid or solid medium that facilitates ion movement between the electrodes. Composition affects conductivity and thermal stability. Current collectors, made from copper, anode, and aluminum, cathode, these layers transport electrons to the external circuit. Number 3. Battery cell design considerations. Energy density, the amount of energy stored per unit weight or volume. Higher energy density improves the range of EVs. Thermal management, effective dissipation of heat to prevent thermal runaway. Incorporation of heat-resistant materials and cooling systems. Safety features, pressure relief vents, shutdown separators, and flame-retardant electrolytes reduce the risk of fire or explosion. Longevity and durability, materials and designs optimized to withstand thousands of charge-discharge cycles. Packaging efficiency, balancing compact design with thermal and mechanical stability. 4. Advances in battery cell architecture. Solid-state batteries replace liquid electrolytes with solid alternatives, enhancing safety and energy density. Bipolar designs stack cells with shared electrodes to improve energy density and reduce material use. 3D electrode designs increase surface area for faster charging and higher capacity. Battery cell manufacturing. Manufacturing battery cells is a highly precise and complex process that involves multiple stages, from preparing raw materials to assembling the final cell. Each step is critical to ensuring the performance, safety, and longevity of the battery. 1. Overview of the manufacturing process. The battery cell manufacturing process can be broadly divided into 3 key stages: electrode preparation, cell assembly, formation, and testing. Electrode preparation. This stage focuses on creating the anode and cathode, which store and release energy during the battery's operation. Mixing. Active materials, e.g. lithium compounds for the cathode, graphite for the anode, are mixed with binders, conductive agents, and solvents to create a slurry. Precision is critical to ensure uniform consistency and optimal performance. Coating. The slurry is applied onto thin metal foils, aluminum for cathodes and copper for anodes, using advanced coating machines. Uniform coating thickness ensures consistent performance. Drying. The coated foils are passed through drying ovens to remove solvents, leaving a solid electrode layer. Calendering. The dried electrodes are pressed between rollers to achieve the desired thickness and density, enhancing conductivity. Slitting. The electrodes are cut into specific sizes and shapes suitable for the cell design: cylindrical, prismatic, or pouch. 3. Cell assembly. This stage brings the electrodes together with the separator and electrolyte to create a functioning battery cell. Layering. Alternating layers of anode, separator, and cathode are stacked or wound depending on the cell type. Cylindrical cells, rolled into a jelly roll structure. Prismatic cells, stacked in a rectangular arrangement. Pouch cells, stacked and enclosed in a flexible pouch. Electrolyte filling. Liquid electrolytes are injected into the cell to enable ion movement. Solid electrolytes are integrated during the layering process in solid-state cells. Sealing. The cell is sealed to prevent leakage and exposure to moisture or air, which can degrade performance. 4. Formation and testing. This stage activates the battery and ensures it meets quality standards. Formation. The cells are charged and discharged under controlled conditions to stabilize the electrode materials and form the solid electrolyte interface, SEI layer. This step ensures the battery's longevity and efficiency. Testing. Cells undergo rigorous testing for capacity, voltage, resistance, and thermal stability. Stress tests identify potential defects or weaknesses. Aging. Some cells are stored for a set period to ensure consistent performance over time. 5. Automation in manufacturing. Battery cell manufacturing is heavily automated to improve precision, consistency, and efficiency. Advanced robotics and AI-driven quality control systems are employed to detect defects and optimize production.
Battery pack assembly. Once individual battery cells are manufactured, the next critical step is assembling them into battery packs. This process involves combining cells into modules and integrating these modules into a complete battery pack, equipped with safety, thermal management, and control systems. 1. Overview of battery pack assembly. A battery pack is a structured arrangement of cells, the smallest energy storage units; modules, groups of cells connected in series or parallel to achieve the desired voltage and capacity; pack, the complete system, including modules, thermal management, housing, and control systems. 2. Steps in battery pack assembly. A. Cell sorting and grouping. Cells are tested and sorted based on their capacity, voltage, and internal resistance to ensure uniform performance. Matching similar cells reduces imbalances and extends the pack's lifespan. B. Module assembly. Cell connection. Cells are connected using bus bars, tab welding, or conductive adhesives. Series connections increase voltage, while parallel connections increase capacity. Encapsulation. Cells are secured in frames or enclosures for mechanical stability. Electrical insulation ensures safety and prevents short circuits between cells. C. Pack integration module arrangement. Modules are arranged within the pack structure, typically in a rectangular or cylindrical layout. Battery management system, BMS, integrated to monitor and control voltage, current, and temperature for optimal performance and safety. Thermal management system includes cooling plates, liquid cooling channels, or phase change materials to regulate pack temperature. Wiring and connections. Electrical connections link modules to the BMS and external terminals. Enclosure. The pack is enclosed in a durable housing, often made of aluminum or composite materials, to protect against physical damage and environmental factors. 3. Thermal management. Maintaining an optimal temperature range is vital for battery safety and efficiency. Systems include liquid cooling, circulates coolant through channels or plates to remove excess heat. Air cooling uses fans or natural convection, typically in lower capacity packs. Phase change materials, PCMs, absorb and release heat during operation to maintain temperature stability. 4. Safety features. Battery packs are equipped with multiple layers of safety systems. Fuses and circuit breakers protect against overcurrent and short circuits. Pressure release valves vent gases during abnormal conditions to prevent explosion. Fire-resistant materials minimize the risk of fire spreading within the pack. Crash protection, structural reinforcements to withstand impact in collisions. 5. Quality control and testing. Electrical testing verifies the performance of cells, modules, and the entire pack under load conditions. Thermal testing ensures the effectiveness of the cooling system and resistance to overheating. Mechanical testing assesses the pack's durability under vibration, shock, and compression. Environmental testing evaluates performance in extreme temperatures and humidity. 6. Innovations in battery pack assembly. Modular designs. Standardized modules allow for easier assembly, maintenance, and upgrades. Wireless BMS eliminates wiring between modules, reducing weight and complexity. Integrated cooling systems, embedding cooling channels directly into the pack structure for improved efficiency. Recycling-compatible designs, packs designed for easier disassembly to recover materials for reuse. Quality control and testing. Quality control and testing are essential stages in EV battery production to ensure the safety, reliability, and performance of the batteries. Since EV batteries operate under demanding conditions, rigorous testing is conducted at every level, cells, modules, and packs, before they are deployed. 1. Importance of quality control in EV batteries. Safe prevent hazards such as thermal runaway, leakage, or short circuits. Reliability. Ensure consistent performance over the battery's lifespan. Compliance. Meet regulatory standards and industry certifications. Consumer trust. Build confidence in the safety and longevity of EVs. 2. Levels of testing. Quality control measures are applied at multiple stages during the battery production process. A. Cell level testing capacity. Testing measures the cell's ability to store and deliver energy over charge-discharge cycles. Voltage testing verifies the cell's voltage stability under various conditions. Resistance testing determines internal resistance affecting heat generation and energy efficiency. Leakage and seal integrity ensures no electrolyte leakage and proper sealing of the cell. Thermal testing evaluates the cell's behavior under high and low temperature conditions. B. Module level testing voltage matching ensures cells within a module are balanced to avoid performance issues. Thermal uniformity tests for consistent heat distribution across cells in the module. Vibration testing simulates road conditions to assess structural integrity. Mechanical strength tests the module's resistance to physical shocks and impacts. C. Pack level testing. Load testing simulates real-world energy demands to measure performance under load. Thermal management validation verifies the effectiveness of cooling or heating systems in regulating pack temperature. Short circuit and overload testing ensures the pack's safety systems respond correctly to electrical faults. Crash simulation assesses the pack's structural resilience during vehicle collisions. Environmental testing tests performance under extreme conditions such as high humidity, freezing temperatures, or high altitudes. 3. Types of tests. Electrical testing evaluates capacity, voltage, current, and state of charge (SOC) parameters. Thermal testing monitors heat generation and dissipation to prevent overheating. Mechanical testing includes compression, vibration, and drop tests to simulate real-world impacts. Cycle testing, repeated charging and discharging to gauge the battery's longevity. Safety testing tests for thermal runaway, overcharging, and puncture resistance. 4. Key quality control processes. Formation process, initial charge-discharge cycles to stabilize the battery and form the solid electrolyte interface (SEI) layer. Aging tests. Batteries are stored and tested over time to ensure long-term performance. Automated inspections, use of AI and robotics for precision inspection of components and assemblies. 5. Industry standards and certifications. UL 2580 covers safety requirements for rechargeable batteries in EVs. ISO 6469 provides safety specifications for onboard rechargeable energy storage systems. IEC 62660 addresses performance and safety testing for secondary lithium-ion cells. SAE J8464 tests for abuse tolerance, including mechanical and electrical stress. 6. Common challenges in quality control detection of micro defects. Small imperfections can lead to significant performance or safety issues. Testing scalability, ensuring consistent testing at high production volumes. Thermal management validation, simulating real-world conditions for comprehensive thermal testing. Cost of rigorous testing, balancing quality assurance with cost efficiency. Recycling and sustainability in manufacturing. The rapid adoption of electric vehicles, EVs, has highlighted the need for sustainable practices in battery manufacturing. Recycling and sustainability efforts not only address environmental concerns, but also help create a circular economy, ensuring the availability of critical materials for future production. 1. The importance of recycling and sustainability resource conservation. Critical materials like lithium, cobalt, and nickel are finite. Recycling reduces dependence on mining and ensures a steady supply. Environmental impact reduces the carbon footprint of battery production by minimizing energy-intensive mining and processing activities. Cost efficiency. Recovering materials through recycling is often less expensive than sourcing raw materials. Waste management prevents hazardous waste from battery disposal and mitigates pollution risks. 2. Recycling processes for EV batteries. Several methods are used to recycle EV batteries, each with its advantages and limitations. A. Pyrometallurgical recycling process. Batteries are smelted at high temperatures to extract valuable metals like cobalt, nickel, and copper. Advantages: simple and established process, can handle large volumes of batteries. Disadvantages: energy intensive with significant carbon emissions. Limited recovery of lithium and other light materials. B. Hydrometallurgical recycling process, uses chemical solutions to leach out metals from shredded battery materials. Advantages: higher recovery rates for materials like lithium and cobalt. Lower energy consumption compared to pyrometallurgy. Disadvantages: requires precise control of chemical processes. Generates chemical waste that needs treatment. C. Direct recycling process, retains and refurbishes intact battery components, e.g. cathodes, for reuse. Advantages: maintains material structure, saving energy and costs, potentially the most sustainable method. Disadvantages: requires advanced sorting and minimal material degradation. Conclusion: The production of EV batteries is a cornerstone of the global transition towards sustainable transportation. From sourcing critical raw materials to designing advanced battery architectures, and from implementing rigorous quality control to embracing recycling and sustainability, every step in the manufacturing process is pivotal to creating efficient, reliable, and environmentally responsible energy storage solutions.